Hi everybody. In this video we're going to take a look at the diode curve, and this graph is going to give us an indication of how the diode functions. So the diode curve shows the relationship between the voltage across the diode and the current through the diode. And one thing I want you to notice there is that my voltage line can have positive or negative voltage. So I can be either forward biasing the diode or reverse biasing the diode. So the diode, if I draw the symbol of my diode here, if I apply a positive voltage to this side, negative that side, that's going to be the forward bias condition. Okay, so we've forward bias, that's going to be this half of the graph. And if I reverse that, then that's reverse biased, and that's this half of the graph. And actually, let me redraw these down below so that we have them down there, and then I can erase them from above. Okay, so when we're in the forward bias condition, when we've got positive voltage at the anode, negative at the cathode, until that voltage reaches a certain point, we're not going to get barely any current flow. So we're going to see something like this. But eventually, that current will be able to grow, increase quite rapidly. And this voltage here, we'll say some barrier voltage. And for a silicon diode, it's roughly 0.7 volts. Okay, it's different for germanium diode, which is more like 0.3 volts. But we're going to assume 0.7 volts in our class calculations, so silicon diode. And you notice that at this point, the current can start to increase rapidly. So usually, well, always, when we have a diode in the forward biased condition, so with a positive voltage here, we want to make sure we have a load resistor in this circuit so that we have some resistance, something to limit the current through this resistor. Okay, so from the diode curve alone, you can see that the diode is capable of supporting lots of currents around this voltage range. What the actual current is going to be depends on this resistor that you use in your circuit. Depending on that R, you're going to be somewhere along this graph. But the thing to note is that you're not going to get that current flow until the voltage here across the diode is above this 0.7 volts. And that, you know, saying above 0.7, that's using an approximate value. As you can see, this is really a curve. So there's a range of values here, and it's not linear, but we're just going to make, in our circuit calculations, we're just going to make an assumption that it's 0.7 volts. Okay. Now for the reverse bias case, if your diode is reverse biased, so the anode is more negative than the cathode, that puts you on this side of the graph. So your voltage is negative with respect to the cathode. And you're not going to see any current flow until what we call this breakdown voltage. And at that point, your diode is broken down and is allowing current to pass through in that other direction. Normally, we don't want to operate in that breakdown condition because you've broken the diode at that point. In the reverse bias condition, we want to operate in this region where the diode is simply stopping current flow. Okay, and then in the forward bias case, generally we're operating, you know, somewhere in this region depending on the resistance in our circuit. So In this forward bias circuit here, if I forward bias the diode, I get some current flowing like this. If I were to draw that circuit with the diode reversed, so now the diode is reverse biased. Oh, let me put my resistor in there. There's my resistor. You would actually see with this diode in the reverse bias case, there is no current flow. Okay, and that's provided that this V in is not exceeding the breakdown voltage of our diode, right? We don't want our diode to have to sustain a voltage there larger than what it is capable of.